Okay, so hello everyone. Sorry for the delay. Uh, okay, so maybe the first question is: have you tried to solve the problems I've sent you? Hmm? Ah. Mm. Ah. And what was the result? Like, could- Mhm. Mhm. Yes. Oh, but when we talk about coefficients, the coefficients in front of linear terms can be put equal to 1 just by scaling. And for second order derivatives, the only thing that matters is overall sign, like for each. Yeah. Uh, if you have an equation of the form, for example, question of u plus dt u plus c u equals to 0, we can get rid of this. If we have first order derivative, we can get rid of this term by scaling this u by time dependent exponential, like u equals to e to the minus c t u tilde, and then this the derivative of this term gives precisely this one with the opposite sign, and this functions solving this equation. So, was this the question? Of course. And this is what we proved on the first lecture, then, that any equation with first and second derivatives, any linear equation with constant coefficients, can be reduced either to this form, probably with some minus signs in the Laplacian, or to equation without this term, but with this term, or to a equation with these two terms. So, mm. Uh, Maybe it's better to find the change of coordinates because it's not so hard. So let me think. Mm, No, probably it's better to compute the change of coordinates because, in principle, you don't know naively what happens with this first order term because, in principle, you could get not dt but, for example, dx, and in this case, it would mean that this derivative can be completely removed. So of course it can be formulated in some invariant way, because you have some quadratic form and you have some vector, and there are some relations between this quadratic form and vector, like is it a in the kernel or not. But maybe it's easier just to find the change of coordinates. And if speaking about eigenvalues of the quadratic form, you are actually demanding a little bit too much, because if speaking of quadratic forms, in principle, we can do arbitrary changes of coordinates, like how to say it. So we have quadratic form of the form x transposed some g x. And for example, we can say that we have two quadratic forms, g1, and another quadratic form is, for example, just x transposed x, or let us say g2x. So generic problem which can be solved is the following. So if we are given with two quadratic forms, we can put them to some canonical form. And what can we do with these quadratic forms? So we have this transformation. So the transformations are x goes to t times x, where this matrix T is from GLN. It's arbitrary matrix, arbitrary change of coordinates. And this transformation transforms G1 and G2 to T transposed G1 or 2 T. And this is an arbitrary matrix. And in principle, we can do the Gram-Schmidt procedure, which gives us some triangular matrix T. And these transformations I'm not sure about spelling, but probably this one. This can bring, so if G2 was a positive definite, for example, it can make this G2 equals to just 1. And after you do this, you can ask for transformations which preserve G2 but transform G1 somehow. So now G2 should be preserved. It means that T transposed times T equals to 1. And it means that this T lies in the group ON, and this group is still big. Like if we have n squared parameters space here, this space is n times n minus 1 over 2 parameters. And then using these orthogonal transformations, we can still bring G1 to canonical form, namely, if we just diagonalize this G1 and it has different eigenvalues, we can do this with orthogonal transformation, and this G1 will be so I don't know, maybe it's better to write like this. So we can transform, we can make G2 equal to 1, and then this G1 can be brought to diagonal form with some eigenvalues, lambda 1 and so on, lambda n, which can be positive or negative. So the point is that if we are talking about eigenvalues of quadratic form, it means in reality that we are talking not about just one quadratic form, but about pair of quadratic forms. And if we want to think about, because we can bring one quadratic form to this identity form and another to a diagonal form. So no, they are quadratic forms. We cannot commute quadratic forms because if you quadratic form is an element of the vector space V V star tensor V star. Or in other words, it's isomorphic to homomorphism from V to V star. These two spaces are different, and we cannot multiply or commute operators between V and V star. So, but this quadratic form gives the identifications of these two spaces, and if you want something that can be something that is an operator from the space to itself, we should take the difference, or we should take the ratio of these quadratic forms, like G1 times G2 inverse is in home from maybe, sorry, what is better, maybe G2 inverse times G1 is an element of homes from V to V. So it means that this ratio acts from the vector space to itself. And this ratio, since it's an operator, it has eigenvalues. And because it transforms the operator, for example. So G2 inverse G1 transforms as T inverse G2 inverse G1 T. So it transforms, like you can check it from this transformation laws. So since it's an operator, it has eigenvalues. For example, we can formulate it differently. The determinant of lambda times 1 minus G2 inverse G1 is invariant. So these eigenvalues which we obtain in this procedure of finding canonical form of two quadratic forms, these eigenvalues are actually eigenvalues of the ratio of two quadratic forms. So the main message is the following. If we have just one quadratic form, it does not have continuous invariance. It can be brought to sum and difference of squares. And if we work with complex numbers, we will have just sums. We will have just a sum of squares and some zeros. And if you have two quadratic forms, there are these discrete invariants, and there are also n continuous invariants, namely the eigenvalues of the ratio. Actually, I'm not quite sure what precisely happens for the real numbers and arbitrary signatures. Probably it needs some investigation, but the general picture is of this kind. But if you work with these differential operators, we have only one operator, so one quadratic form, and it does not have continuous parameters. So is it clear?
Suppose that on the complex numbers we can also change the sign of the eigenvalues. We can take them for two or ones, but while on the real numbers we cannot, and we just do ones and ones and zeros.
Yes, of course, because like x squared minus y squared is x squared plus I y squared. So, but I would not call this eigenvalues because eigenvalues are invariants of a pair of quadratic forms. So,
So when we talked in previous courses about eigenvalues on a quadratic form, we implicitly included the idea of taking the identity as the other quadratic form.
yes. So eigenvalues appear either if you try to diagonalize quadratic, if you try to diagonalize a pair of quadratic forms, it's one situation. Another situation, which is actually equivalent, we just forget about the second quadratic form, is when you try to diagonalize quadratic form with orthogonal transformations. So. Oh, by the way, sorry, I forgot. What was your name?
Alex.
Thank you. Probably I was ask all the others because I forgot most of the names. So, and what is your name? Thank you. So I remember the list, but I don't remember. Who is who? So, are there any questions about these problems? So, let me maybe remind you what we were doing the last time. So, we've introduced the Fourier transform, which looks like this. So, Fourier transform of a some of a function of x, where this x was in z over z and 1 times z over z and 2 was given by sum of k e to the 1 over and 1 and 2 . and we proved that where this k is to say it, when n1 k1 n2 k2 were integers. Again, z over z and 1 times z over z and 2. So we proved that the inverse Fourier transform is given by this formula. Do you remember, did I use on this signs or on the opposite? Probably this. Did I use this signs or? So, and using this Fourier transform, we solved this discrete Laplace equation, like Laplacian of u equals to f, where this Laplacian was a two-dimensional Laplace operator that was t1 plus t1 inverse plus t2 plus t2 inverse minus 4. And there were shift operators, and the answer for solution was that u tilde of k was f tilde of k divided by 2 cosine of p k1 plus 2 cosine of 2p k2 minus 4. So we just substituted here the Fourier transformations and checked that it works in this way. So, is it okay? And so we had two ideas concerning the solution of this equation. One idea was to perform the Fourier transform in order to kind of make this operator diagonal and then solve this equation. And another idea was that we can try to naively invert this operator and find find the solution. And to invert it on the space function with their sum of all values, we need to solve an equation that so this was about Fourier transform, and this is about green function. We need to solve an equation that Laplacian in x acting on the green function of two variables x and y equals to delta of x and y. This is delta chronica, which is 0 when x is different from y, minus 1 over and 1 and 2, like this. mm, which uh, which is equivalent to the equation that a product of Laplacian and this green function is identity operator on the space of function with zero sum of values.
If we omit the minus 1 over and 1 and 2, okay, the second part of the we still get the identity of V prime.
But
actually is the identity of the whole space.
But well, if you act with this operator only on functions which have zero sum of all values, then it is true we will get an identity. But I want to have this green function as a function on the whole space. In a sense, it's a space of a matrices n1 times n2 by n times n1 times n2, and I want to have some explicit matrix. Like so, there should be some equation which makes sense in this space of all matrices.
So it is a kind of pseudo inverse.
Yes. Yes.
We kill the kernel of the Laplacian and we remain with.
Yes. Yes. Actually, it is quite a typical situation, even in the infinite dimensional case, because it is usual, but not in this Laplacian case, but for the wave equation, it is typical that equation with zero right-hand side has some solutions. So. Okay, so if we now combine these two ideas and try to use Fourier transform to compute the solution of this equation, what we get? So Fourier transform of this delta minus 1 over n tilde is what? It is, according to this definition, a sum over x delta x y minus 1 over n n1 n2 1 2 e to the minus 2 pi I k x. So the first term is non-zero only for one value when x equals to y. So it gives e to the minus 2 pi I k times y. And the second term is non-zero only when k is non-zero, because otherwise the sum of these exponentials is zero. They are roots of unity, and their sum is zero, as we checked. So, and when k equals to 0, we have n1 times n2, which means which is cancelled with this one, and finally we get
we are computing the Fourier transform of the second term in x.
Yes, of this one.
Okay. We're transforming in x or in y, which is the same.
Almost. It depends on the difference of x and y. So yeah. So this is delta k0. Mm. So the Fourier transform of this green function is obtained by division by the denominator. And if we try to do the inverse Fourier transform of the green function, then we get that g of x and y, x and y equals to let us first write the Fourier transform like the Fourier transform in the variable x is given by so did I forget something on or not? I know it's fine. And now if we try to compute green function in the coordinate space, we need to do the Fourier transform with this expression. So in j of x and y equals to sum over k 1 over n1 and 2. And now let us combine these two exponential, the one which is in the definition of the green function and this expansion.
That one should be the Fourier transform of the Laplacian applied to G and not.
Sorry, I forgot to divide by by the most essential part.
Okay.
So it is the sum 2 pi I k x minus y. And here is 2 cosine of 2p k1 plus 2 cosine of 2p k2 minus 4. So minus delta k0. And it is in some sense the answer, because we now have an explicit expression for the green function, and if we are given with arbitrary right hand side, we can just take sum over y and get a solution of this Laplace equation. So technically, it's a little bit better than to write this matrix and compute its inverse, because it contains only one summation. It's some explicit sum, and it's more efficient from the computational point of view. But I'm not sure. Probably in this discrete case, we cannot do anything more with this green function. Like I think we cannot compute the sum, and it's possible only in the continuous case. And also we can see that this subtraction of delta Kronecker was important because otherwise the sum will contain pole at k equals to 0. Because 2 plus 2 minus 4 is 0, and in this form it cancels.
So if we apply G to F, we get the solution we get from the calculation.
Yes, so if you have this gain function, it means that a solution of the equation u of x is given like if you have this equation delta Laplacian of u equals to f, then the then solution is given as u is sum over y in z over z and 1 times, as usual, g of, so u of x, g of x and y times f of u, f of y. So in this one, it means so it means basically what was written in the right hand side, that gain function, at least this gain function, is in the inverse to this Laplace operator. So 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 of course we should tell precisely what is the inverse and so on, but general principle is the following. Also about the green functions. So here we consider this maybe a little bit artificial problem on a torus, just to avoid all these questions about the boundary and thanks to this choice of boundary conditions, we could also make this Fourier transform quite easily. But and the problems which usually appear are problems with some boundaries. And let me tell you what are the differences in these cases. So the most natural example of a problem with a boundary is some rectangle. So now we put this lattice not on a torus, but just on a plane, and again consider some x1 from x1 will be from maybe from 1 to n1, x2 from 1 to n2. But if we have boundaries, so this Laplace operator contains shift operators to the left, to the right, to the top, and to the bottom, and we should have this equation satisfied in all this. Let us maybe call this this set by letter D, which means domain. It's some finite set which contains again n1 times n2 points. So we should have on this Laplacian equation, Laplacian of u equals to f, Laplacian u of x equals to f of x for x in D. But there is the following question: if we consider a function in some point close to boundary, and this Laplace operator involves shift in this direction, the direction of boundary. So to define it, we need to say what is the value of our function u in this boundary points, which I denote by crosses. So we have this internal, and we also have a boundary, like which we denote by so. So these points lie on the boundary, and we denote them D, which is boundary. So a well-defined problem in this boundary has this form. So first we need to say what is the Laplacian of u inside this domain, and also we need to say what is the value of u on the boundary. There is some f, what is called f b of x when x is in the boundary of D. So is clear? There are also there can be also some strange boundary conditions, like we can say that this value of function on the boundary is some linear combination of the value of function inside plus some constant, and it is an analog of boundary conditions involving derivatives in the differential case. But nearly we can think on this way. And we see that also in this problem it is quite natural to substitute boundary values how to say it? Okay, so first I need to say that since this equation is linear, we can try to separate a problem about boundary and a problem about internal part of D. So maybe it's, I don't know if we call this a theorem, but it's just some simple statement that a problem can be split into two. namely, we can solve separately one problem with Laplacian of u1 equals to f of x for internal part, and u of x is zero on the boundary, and it's u2, and oh, sorry, it's u1, and the same for some other function u2 equals to 0. Equals of boundary on the boundary. And so these two problems will have a solution. And now the question: if we have solutions of these problems, how to get the solution of initial problem? So u equals u1 plus u2 solves the initial problem. And so it's kind of a first step. And now, if we want to find this solution, we can do the same procedure. Like in this problem, we can find find the gain function. Laplacian of g should g of x y should equal to delta of x y. In this case, we can ask just for this because now the kernel of this Laplace operator is 0. So who knows why it is 0? Yeah, of course, it is a related question because if it is a non-positive definite, then we can get plane waves, which we'll see later, which in the kernel, a lot of them. But even in the positive definite case, we had one element in the kernel. It was constant function because
since we have the boundary condition, the only constant function satisfying the equation, and the boundary condition is the zero function.
yes, yeah. So the argument was the argument to us was that because of the nature of this Laplace equation with the right-hand side, it told that the value of function in the middle is the average value of a function in four neighboring points. And if we apply this argument for the domain with boundary, it will mean that this function cannot have a minimum or maximum inside the domain, so it has it on a boundary, but boundary values are zero. So it means that it is zero everywhere. And it's also the same situation in the differential case. So the only function in the kernel of Laplacians is constant if we are living in the finite domain with zero boundary conditions. So here we just
In this case, it is clear to me why, in general, if we have a Laplacian of u equals 0, then the function should be constant, as we showed last time. But in that sense, a sort of continuity of the function came out, despite not explicit in it. But in this case, we have the condition on the boundary that is 0. But couldn't we consider a function that is constant equal to c on the domain and then equal to 0 on the border? Because in that case, it surely wouldn't be continuous, but it would solve the problem.
No, but what do we call continuity in this discrete case? So we have just independent values of functions of function in all these points, and there is this discrete condition. So, for example, if you say that it is constant inside and 0 on the boundary, you can consider some of the boundary points. It will have, for example, 3, 2, or even 1 neighbor where its value equals to constant, and 1 point where its value equals to 0. But the value inside equals to the average value of all neighboring points. So if at least one of them is 0, it means that we cannot satisfy this condition.
So with that method, we extend the boundary this constant.
Yes. So, and we get that the only function in the kernel is 0. And so if we want so this problem can be solved. And if you want to solve this problem, we can do exactly the same as here. We can try to find some other green function so that like another green function. Maybe we can call it boundary to bulk. So to bulk, like internal part. So this is probably a physical jargon, or maybe mathematicians also use it. So this internal part is sometimes called bulk. So this green function solves the equation. So sorry, I forgot to say here that this green function should also satisfy boundary conditions, like g of x y is 0 when x is on the boundary. So, and this gain function, which you can call GB of xy, should satisfy this equation with zero boundary conditions, and um, GB of x y equals to delta of x y when x is on the boundary of this domain. So so the structure of solution to this boundary problem will look like this. Solution. U of x will equal to sum over internal points. Oh, sorry, y inside D of xy f of y. This is a solution for u1 for one problem, plus sum over y inside boundary g boundary of x y f boundary of y like this. So I don't want to find this green function, especially the second one, in this discrete case, because probably it's a bit more complicated than in the differential case. But in differential case, these two functions are literally the same function. Applied in different ways. So we will derive it when we switch to the actual differential equations, where there's some analysis and so on. But here we just say that there are some Green functions which solve these equations. But for example, if you want to find this gain function in a similar way, we can still use the Fourier transform, but we need to modify it a little bit. So we see that here everything was shift invariant, and it was natural to use just exponentials to represent any function on this circle. But if we are on this finite domain, we can do some modification with the Fourier transform. So probably I can write this. So our set of points is now from uh, from 1 to uh, 2 and 1. Maybe it's better to consider just one-dimensional Fourier transform, because other cases can be obtained just by adding extra variables. Mm. And we can also put here point 0 and point n1 plus 1. So we are considering functions which equal to 0 at 0 and also equal to 0 at n plus 1. Maybe just put here n. So in this case we use the exponentials, and if we want to still have some combinations of exponentials, it's quite natural to try to choose sign functions. So let us try to choose functions like phi k of x equal to a sine of 2 pi k times x. So not 2 pi, maybe 2 pi is fine. Yeah.
Okay, with the same properties before, so that k times n is an integer.
No, let us check this carefully now. So when k equals to 0, or when x equals to 0, this phi k of x is 0. It is fine. But we should also satisfy another boundary condition. We should have a phi k of n plus 1 equals to 0. And this means that n plus 1 times k should equal to maybe 2 times n plus 1 times k should equal to, or should be integer number. Right? So it means that now k's in this formula go from from 1 maybe let me write it 1 over 2 n plus 1 2 or 2 n plus 1 and so on. N over 2 n plus 1, like this. So yeah, so we can say that our function f(x) can now be expanded over these sign functions. So is sum probably 1 over. I'm not sure which is the correct coefficient to choose here. Maybe just forget about this coefficient. Times f tilde of k over k in this set. And we can think about this formula in the following way, that if we want some function which is 0 in this boundary points, 0 and plus 1, you can imagine it as a function which is defined on a circle, but with a boundary condition. Maybe better to say with a symmetry condition. So this is 0, 1, and so on, n plus 1. And at this point will be so maybe 2n plus 2. So is it correct? Yes, probably. Yes. So we have n 2n plus 2 points in total. So we can say that these functions on these boundary conditions are equivalent to functions such that f of x equals f of minus x, and f of x plus 2 and n plus 2 equals to f of x. So the space is equivalent to space of functions which are 0 in these 2 points, because a condition that f of 0 is equal to 0 follows from this antisymmetry condition. And so these signs are basically combinations of exponentials which live on this whole circle. But the question is why this Fourier transformation with sign functions is useful for our purposes. Like, why is it useful for a solution of the Laplace equation? The answer is the following. So this sign is not an eigenfunction of of t, of the shift operator. Mm. Hmm?
Why does that condition is equivalent to f0 equals to 0 equal to f1?
Because f of x equals f of minus x says that f of 0, sorry, minus f of minus x, sorry. So this one says that f of 0 is equal to 0, and uh, if it is so, um, and also, if we consider f of this opposite point, f of n plus 1, we can also say that f of n plus 1 equals minus f of n plus 1. This is from antisymmetry condition. And from this periodicity condition, it equals to uh, uh, sorry, it equals to, yes, it equals to minus n minus 1. This is from antisymmetry. And from periodicity, it equals to minus f of n plus 1. So, welcome. So this is also 0, and all other values are independent. So this space of functions on the interval can be embedded into the space of functions on a circle. And it's again the same in the discrete and in the continuous case, because we can do the same with the functions of continuous variable. Yeah, so now this function sine of 2 pi kx is not an eigen function of t. But let us check what happens if we take t plus t inverse. Namely, let us act with the sum t plus t inverse on one exponential, e to the 2 pi I kx. So who can tell what will be the result of this action?
E to the 2 pi I k x plus 1 plus
But if we pull these constant factors outside the function, so
pi I x.
k, it's tx, tx plus e to the minus 2 pi I k, e to the 2 pi I x, kx. So we see that this eigenvalue is is the same for k and for minus k. So we can say that now if we act with this operator on the opposite exponential, tx inverse to the minus 2 pi I kx, it will give the same eigenvalue. So this eigenvalues equal. And this means that we can use this Fourier transform on a finite interval to solve a Laplace equation on this interval. And so it should be.
Actually, the eigenspace has dimension 2, so we can change the basis.
What do you mean by dimension 2?
The eigenspace of the eigenvalue of e to the 2 pi I k plus e to the minus 2 pi I k is the span of e to the pi I kx and is opposite the exponential, and I can change the base of the eigenspace using sine and cosine.
Yes, precisely. And so actually, let me think about the cosine. So in principle, if you want to solve this boundary problem, there is some hint here. So such wait, let me think for a while. No, probably I'm not ready to think about this boundary again function. In this case. Yes, but here we are interested only in one combination of these exponentials because we also have these boundary conditions. That function is 0 on both boundaries. So I also forgot to make another comment about the Fourier transform. So let me think. Probably I can erase on this one. So are there any questions about this story, about the Fourier transform on a segment? If no, let me go back to this formula. So, we saw that a solution of this equation is written in the Fourier space in this way, that a solution equals to some function times some other function, which is a Fourier image of a gain function. And we also saw that if you try to compute this gain function in coordinate space and apply it to our problem, we get a formula. Formulas of this kind, that u of x equals to sum over y, g of xy times f of y, and so on. So I would like to ask the following question. So suppose that there is a formula, like product, that some function equals to the product of some Fourier image of some function equals to a product of Fourier images of some other functions. U of x equals to g tilde of k, or sorry, u of k equals to product of g tilde of k times f tilde of k, right? So in the Fourier space, it is just product. And the question is, what happens in the coordinate space? So we have this formula, and we want to express u of x in terms of g of x and f of x. So is this question clear and natural? So let us do it in a stupid way. Namely, compute u of x as sum over k 1 over 1 and 2 e to the 2 pi I k times x. Now substitute each of these Fourier transforms as Fourier transform. So this is sum over x. Oh no, not x, sum y. G of y times e to the minus 2 pi I y k. Here the same, sum over some z, f of z e to minus 2 pi I, sorry, y k. Z k. So we have now this sum of our three variables, and we have a product of three exponentials. So let us put all this together. So it is 1 over and 1 and 2 sum over k e to the 2 pi I k x minus y minus z times g of y times f of z. And now, of course, there is another sum over y and z. So can we compute this first sum in k? What do we get? So, so you remember these vectors are integer vectors, and this one is such that e to the 2 pi I k1 and e to the 2 pi I k2 are some roots of unity of order n1 and 2. So and this exponential is the only one place where this vector k appears.
It survives only when x is equal to y plus z.
Yes, precisely. Because otherwise, in this case, the sum just 1. And we take it n1 times and 2 times. And if they are different, we have at least one root of unity raised to some power, and we basically take sum of all the roots of unity, like this, and this, which sum to 0. Or we can just compute this geometric progression. So we have sum of y and z, delta of x, y plus z, and g of y, f of z. So we have the sum where sum of the arguments of the two functions equals to x. Or we can write it as a single sum, which is sum over z, g of x minus z, f of z. And this expression is also called convolution, and it is denoted by a star. And this is g star f, dependent, and it depends on point x. And this is called convolution. So is clear. And this is the obvious practical application of this knowledge is that if we switch to Fourier components of some equation and solve it in the Fourier components, we can then go back to coordinate representation and transform such kind of formula to such kind of formula with a green function. So we don't need to do this Fourier transformation again and find the green function. So if you have this, then we automatically have such formula. And this observation also works in the other direction. So so far we used Fourier transformation to solve the difference equation, or it can be differential equation, because the idea is the same everywhere. We find such basis of functions which which is an eigenbasis for shift operators, and then our operator also acts diagonally on this basis because it is a shift invariant. But this logic can be applied to any operator which is a shift invariant. So namely, it can be thought in this way. If some operator is shift invariant, it means that it commutes with the shift operator. But if some operator has simple spectrum, it means that all other operators which commute with it are functions of this operator. And in this way, we have some kind of guarantee that they will diagonalize once we diagonalize the shift operator. So following this logic, we can try to apply this Fourier transformation technique also for integral equations. Namely, it can be done like this. So maybe I can erase this. So suppose that we have maybe. So let me think. If I can I write some simple example. Or maybe let us consider some general statement. So if we have some some integral operator g hat as which acts on a function f by uh, f of x equals uh, to sum or integral. Let us write maybe sum g of x minus y f of y but when I write a sum, it means that in the continuous case, it can be just replaced by integral. So if you have some operator which depends only on the difference of coordinates, we realize that we are precisely in this situation where this is a convolution. So we realize that it is the convolution of g times f, and so in the in the Fourier basis, it is uh, g hat times f equals to oh, maybe maybe let me formulate some problem. For example, we want to find eigenvalues of some integral operator, or in this case, some some finite mm, it's called actually interpolates matrix, some matrix which has coordinate dependent only on the difference of I and j. So we want to find eigenvalues like lambda f equals to lambda f of x equals to sum over y g of x minus y f of y. We want to find such lambda. So if we see something like this, which is translation invariant, we can apply to this Fourier transform, and after this Fourier transform, this equation will transform into lambda times f tilde equals to g of k. equals to j tilde of k times f tilde of k. So the point is that such integral or difference operators which depend only on the difference of points can be diagonalized by Fourier transform. And here we can see that all eigenvalues of this operator are just values of its Fourier transform in different points. So
The difference on the pros, in the sense that we have a circulant matrix and not a Lorentz matrix, or
yes, probably. Yes, it should not be called Aristotle's matrix. It's this. Is it called circular matrix?
yes,
Mm-hmm. Ah. Yes. So it's, for example, for finite matrices, but it.
for example, if you have band stopits but with zeros outside the band,
Mm-hmm.
that one is not diagonalized by
Yes. Yes. True. Mm-hmm. So. Mm, and now there is also another thing about Fourier transform I wanted to tell. So far we did not think about the scalar product on the spaces, but it can be defined and it makes sense to define it. And it turns out that Fourier transform is also some natural operation, namely it's a kind of orthogonal transformation or a unitary transformation, I try to say. So we still have these formulas for a direct and inverse Fourier transform. And now let us define the scalar product um, on our space of functions. It can be it can be done naturally in this way. F1 times F2 is sum over x F1 conjugated of x times F2 of x. So I don't know, I don't remember how it is called, but maybe it's called unitary scalar product, so that lambda f1 f2 equals to lambda bar f1 f2, and f1 of lambda f2 equals to lambda f1 f2. So Okay, what's going on with ventilation? For some reason it's off again. Okay. Uh, yeah, so there is this scalar product. It's obviously non-degenerate because uh, a scalar product of f with itself uh, is greater or equal than 0, and it equals to 0 only when f itself is equal to 0. So well, there is this scalar product, and we can now present one orthogonal basis for the scalar product. Uh, like if you take delta functions, uh, delta y1, consider it as a function of x, delta y2 of x. So what will the scalar product equal to? So this is a function which is non-zero only at point y1, and this is a function which is non-zero only at point y2, and they equal to. Yeah, thank you. So it's actually orthonormal basis. But and what happens if we so it's one basis, and let us now consider e to the 2 pi I k1 of x k1 times x, and e to the 2 pi I k2 times x. What does it equal to? Yes, thank you. So this functions also form orthonormal basis, but with a little bit strange normalization. And if you now look at these formulas for direct and inverse Fourier transform, we see that one formula says that a function f can be expanded over this orthonormal basis, and another formula says that if you want to take individual coefficient of this expansion, we should compute a scalar product with basis elements of this orthonormal basis. But now there is a natural question. So since these two bases are orthonormal, it means that a scalar product which is natural in this coordinate basis will also be natural in the Fourier basis. And let us now try to get its expression in Fourier components. Maybe I can erase this blackboard. So um, uh, so we want to compute the product of two functions in terms of their Fourier components. So we have f1 times f2, which is sum over x, f1 bar of x of 2 of x. Now substitute these formulas in terms of Fourier components. Sum over k k1 e to the 2 pi I k1 x f1 of f1 tilde of k1. This all is complex conjugated times sum over k2 f2 of k2 1 over n1 and 2 squared. And now as before, we take sum over x conjugate of this exponential with the same exponential with the minus sign. So we get sum over k1, k2, 1 over n1 and 2, delta of k1, k2, one tilde of k1, f2 tilde of k2. So we can remove the delta function. Oh, so this one is conjugated. We can just get one sum over k. 1 over n1 and 2, f1 of f2 tilde of k2. So as expected, this this scalar product on the defined basis is also diagonal. And maybe the last remark about this Fourier transform. So it is quite natural to consider equations with real functions, and the question is what it means for the Fourier transform. So how is it reflected? So it is not true that we can just say that f tildes should all be real because we sum them with complex exponentials. So So we should check what is the implication of the condition that f bar of x uh, is equal to f of x. So let us take the formula for the Fourier transform. Like f tilde of k is a sum of f of x e to the 2 pi I kx. And now take conjugation of it. F tilde of k conjugated equals to sum of f of x, again, because it is real, sum minus 2 pi I minus k times x, because it is out of conjugation of this exponential. And finally, it equals to sum or it equals to f tilde of minus k. And this is what is the meaning of reality condition in the Fourier modes. So if you don't like complex exponentials, you can of course change sines and cosines, which will be real functions. But usually it's more convenient to work with functions with this symmetry property. And,
in the last sum, K1 and K2 should be K, right?
Yes, thank you. Yes. Okay, so this was all about Fourier transform in a discrete case in finite domains, and probably will give some problem about this Fourier transforms, so that you can compute all the scalar products and get used to it. And on the next lecture, I'm going to switch to continuous case to some differential equations. And to show what are the differences. Because you see, a lot of ideas work in this finite dimensional case, but there are also some ideas which work only for differential equations.
What is the main and what are the elements of the course? We will study some equations in details, some problems related to heat wave and mass equations, or something else.
Well, basically we will study those three equations, maybe a little bit the Helmholtz equation, but the general idea is this. So we'll study different boundary conditions and so on. Yeah, thanks for attention.